So yes, the microphone's already working. This is good. So at least we have audio now. And I think also the people online can hear it. So now I could start talking, I don't know, childhood anecdotes or something. Or how this work came to be. So because everyone has been asking me, how's my PhD progressing? Not as fast as I would like, because I frequently get distracted with other projects. Like, oh, it's programming, SMD interface for Common Lisp doesn't sound too hard, right? I can do it in a few days. Yeah, and then Hofstadter's law got me. But at least I got something to show for that. ZF microphone. Oh, wow. It's lovely. Yeah. So at least I got something interesting to show, unless they don't allow me to show a thing. The SIMD dance. You could probably hold the talk without the slides. Yes. Oh. No, I can't. I can switch it to 144. Yes, please.
Receiving any output from the HDMI.
Oh, okay.
We've checked everything out.
Okay. So.
It's not even a resolution. It's just we are not receiving any output from your
Okay.
laptop.
Should I try the other one or? Those. Okay. Well. Kada? Maybe we can use your laptop, do you? Because I can show the slides. I was just hoping I could show some live programming. So, or I could send someone my slides.
From your laptop, that seems
Okay.
to be the problem, that your laptop is not sending any output
Mm-hmm.
into a receiver.
Okay, I would just maybe restart on. If that doesn't work, I use another device.
Okay, I wonder if you can,
Yeah, let me.
because you want to make a live demo.
Yeah. So I would try to restart it. Let's see if it turns. Does it matter which cable I?
Not really, no, because
So I'll try this one.
signal or technically just it's just that
Mm-hmm. Oh, is there's a but do you have VGA? You know this very old.
I also have HDMI.
Oh, HDMI. Okay, that would be wow.
You have HDMI?
So oh.
USB-C to HDMI.
Okay, let's try that one. Okay, thank you very much. We're trying. We are trying USB-C to HDMI, which apparently exists. So. This is now USB-C via something. Wow, I think it works. My laptop shows something. Yeah. Unfortunately, I only have 5 minutes left. I try to somehow shorten it. Somehow. Okay. Thank you, everyone. Thanks, everyone, for the immense patience. They say come 15 minutes earlier to check things, but I did. So apparently, you have to come half an hour earlier to check things. Right. This talk is about closing the performance gap between Lisp and C, which is a bold title, and it was a good idea to have a bold title. The paper got accepted, so that's the way to go. What do I mean by performance gap? Lisp is already the perfect language, right? And it is for some cases. So Common Lisp already outperforms most other languages in the good case. I'm just making this claim here, but by good case, I mean cases where you can treat data as code, use metaprogramming, incrementally recompile things. Technically, you could do this in any other language, let's say calling GCC at runtime, using the LSIM, whatever, but in practice, no one ever does. Also things like fully unrolling your Bezier curves, like Paul Graham did on Lisp. Those sorts of stuff. So in the good case, Common Lisp is already fast. But this talk is about Common Lisp in the bad case. Number crunching, image processing, the stuff where people traditionally use C or C++ or Fortran. And the goal is to close this performance gap. So it's not about the good cases, it's about the cases where Lisp really doesn't bring any inherent benefits. And the main issue I identified is there's no easy way to use SIMD instructions in Lisp, and this work addresses the issue. People have asked me what exactly is SIMD. Not everyone is aware, so one slide about that. SIMD is short for single instruction, multiple data. So traditional codes, you have a sequence of instructions, for example, for multiplication, and then you would have 4 successive multiplications, while a SIMD operation would be a single multiplication instruction on an operand that contains 4 values in parallel. And why is this a good thing? You may have noticed that the CPUs are not getting any faster in terms of clock speed. 10 years ago, they had 3 gigahertz. This machine still has about 3 gigahertz. So the clock speed is not going up. And also the instructions that are processed per clock are not going up a lot. So it's still around up to 5 instructions per clock. So there is an upper limit on how many instructions your computer will issue over time. However, thanks to Moore's law, we got plenty of transistors, so we can just make these wide instructions and make SIMD registers and process 4 or even 8 or up to 32 values in parallel with a single instruction, which is messier to program, but you get another factor of 4 to 8 speed up, which you really don't want to miss if you want to go towards high-performance computing. And the first part of my paper and also of this talk is a library called SB-SIMD, which is a convenient SIMD programming interface for Common Lisp. The initial ambition was to have it as a portable interface for all Common Lisp implementations, and then I realized how finite my time is. And so for now, it's on SBCL on x86 64-bit. The good news, by focusing on a single implementation, I was also able to achieve a few nice things. SIMD packs, those operands that contain multiple scalars. They are regular Common Lisp objects you can type off and class off just in the usual way. And also the SIMD functions are fairly generic. It's much better. If you have ever used intrinsics in C, it's a pain to use. Every operand has to match. You have a lot of underscores, long names, all that. This is much easier. They are fairly generic. You have implicit casting and broadcasting of the arguments. Functions like plus, they take any number of arguments, just like the Common Lisp plus. And those functions are safe and convenient by default and fast when necessary. So you can still map car a SIMD function over something, which is then broadcast. It's just not slow anymore, but it still works. But once you have some amount of typing, you also get the speed. And the library is on GitHub, and soon I hope also as a part of SBCL, because it has so many dependencies on SBCL. It should be in the compiler, but we are still discussing what should go in there and what shouldn't. So discussion for afterwards, maybe with a few drinks. Data types. So I've been talking, SIMD packs are just objects, and a SIMD pack is essentially a specialized vector of a certain length. We had to choose a naming convention, and this naming convention is for scalar types, is a single letter that identifies the base type and then the number of bits. So F32, F64, U8, S16 for signed byte 16. The only complaint might be that there is no I for integers, but we found that much more precise. The I is always a bit ambiguous. So U and S for integer types. And the naming convention for SIMD packs is just a dot and then the width in elements. So the product of the bits and the SIMD width should always be 128 and 256 because of restrictions of the hardware. So this is the naming convention. And each such name denotes both a type and a function for coercing an object to that type that makes other things quite convenient. And then there are functions. I won't discuss them in detail because there are hundreds of them, even thousands. But the syntax, the naming convention is that for a function foo, the SIMD equivalent for processing types of x.y is called x.y foo. So, for example, you have f32.4 aref for loading 4 consecutive floating point values into a 4 packs, width for SIMD pack. You have u8.32 plus for adding 32 8-bit integers simultaneously, and so forth. And to illustrate this automatic conversion and broadcasting of the arguments, simple example, if you take f64.2, so double float essentially, and you add it takes any number of arguments, just like the usual way in Lisp, and you add 2, 2, and 4. Each of those operands would first be converted to a double float and broadcast to the width, which is 2. And then added, so what you get is a SIMD pack whose both values are 8. Same for the square root. Something like a 9 would be broadcast to 2 9s, and then you take the root. And also you get error handling. For example, 256 is not an 8-bit integer, so an error is signaled. And there are hundreds of functions for square roots, addition, logical operations. They are described in the paper, also a few macros. What I want to talk about, interesting part about this work is the software architecture. My pro tip is before starting a project, do a back of the envelope calculation, how long it will take you to complete it and whether you have the resources. And I did that calculation. I realized I will never finish this library because there are more than 1,000 instructions in the AVX instruction set alone, and then you have AVX2, SSE, SSE2, SSE3, SSE3 4.1, SSE 4.2, and so forth, and fuse, multiply, add. So a bunch of instruction sets already. If I type all of them by hand, they will contain bugs, and I will never finish. So the solution is, of course, macros and tables in this case. I can proudly claim not a single function in SBCMD was written by hand. It's generated via tables. And I can also quickly show, can I? Now comes the second challenge, whether I can show my Emacs on the screen. I can. Oh. So I can. So this is the code and the instruction sets, and let's have a look at AVX. So it's a very, very long table. It's just a macro, and it contains all the description, and the rest is generated. So you have the assembler mnemonics, the cost, the properties, and so forth. And I can strongly recommend that if you have the opportunity, do something table-driven and don't write repetitive things by hand. I will switch back to the code. Yes, I will show a single example because there's also a second part, and I was already told the time is a bit late. So I hope this is somewhat readable. So this is an example of how you can use the SPSimD library, which is unfortunately not on Quick Lisp, so you have to pull it from my GitHub. And the task here is you want to sum all the positive numbers in a vector. It's artificial. It's just for showing how things work. So the vector is assumed to be of double floats. It's just a vector, so rank 1. And you take an index I, which is 0, and an accumulator, which is a SIMD pack that is also 0 initially, and the result. So this is the ledge binding. Then you have those two type declarations. As I said, each such name also denotes a type. And then the typical pattern in SIMD programming is that instead of having a single loop over the data, you have two loops. One loop that's vectorized with a step size that's the same as the width of the operand, so in this case 4. So you loop with a step size of 4 until you have reached the end of the vector that can be processed in chunks of 4. You don't want to go above. And then you load 4 consecutive elements. You use this f64.4inc. This is a modifier macro that expands into a plus. One speciality, that's why I chose this artificial example, so the f64.4if is not a control flow operator like common Lisp if, because in SIMD it does not make sense. The control flow cannot branch in 4 or 8 different ways suddenly. So instead what it does, all the comparison functions, they return a bit mask that you can then use to select values, to select individual scalars from one or the other provided SIMD pack. So the if actually evaluates both branches and then chooses from either one. Implicit broadcasting is used, so the one argument is just the v, the 4 values that have been referenced by the array. The other is for zeros. And the greater than function generates the bit mask, and the if is used to make the selection. So what we do is we only select values that are bigger than 0. That's why I chose this example. And otherwise, we take the value 0. And then this is added to the accumulator. And after the vectorized loop, you take the horizontal sum. That's just an instruction that's provided to compute the sum of all the elements within that SIMD pack, add it to the result. And then for correctness sake, you process the up to 3 elements that you haven't processed so far. So the remainder loop. And this is a very frequent pattern. It's always, not always, but almost always looks like this in SIMD programming. So I wrote the SIMD library, and it was a lot of work. And then I went on IRC, and I was hoping that people would cheer, but mostly was, whoa, sounds complicated. Can you help me with that? How can you make your code as fast? Or what are the quirks of SBCL? How do you get multidimensional array references fast, and so on and so forth? And I got tired of explaining. I decided, OK, we need more even more abstraction. And this is the second part. It's a loop optimization framework called Lupus that I wrote as so two reasons. One reason was that people have been nagging me about how can you get the fast loops. And the other one is that I need it for my PhD thesis, so it's at least somewhat useful for my actual career. It's a loop optimization framework for Common Lisp, and the main feature is it provides loop optimization as a macro, which surprisingly, it works surprisingly well. And the idea is I want to optimize 80% of the meaningful Common Lisp number crunching loops with 20% effort, because I don't have infinite amounts of time. And the features so far are type inference and specialization, loop invariant code hoisting, common sub-expression, dead code elimination, and of course automatic vectorization. And you can check the code on GitHub. Please don't check when I made the last commits. And how does Lupus look in practice? So I have one example because I also was claiming I want to close the performance gap to C, so I took a very simple example. I hear the people laugh, micro-benchmarks, the compiler people. Yes, which is Jacobi's method. So you take two-dimensional arrays and you iterate over the interior and you take the 4 neighboring points of the source array and you just take the weighted average and write it to the output array, and then you switch the grids. And it's a really simple thing. It can be used to implement something like Gaussian blur. And I wrote one implementation in C, one implementation in Lisp, and the only specialty is that it uses Lupus 4 as the iteration construct. Apart from that, it's perfectly normal common Lisp code. Yeah. So do you still want to, I'm still seeing people studying the code. So I discussed the Lisp code because we are at the Lisp conference. So you iterate over the interior from 1 to 1 minus the end. And then you set the center value to the weighted 0.25, so it's 1/4 of the sum of the 4 neighbors. It's really all there is. And the cool thing is, what does the assembler code of the innermost loop look like that's generated by both GCC and by SBCL? And this is the assembler code. So you may not be aware with x86 assembler, but those functions with the V, those are vector instructions, AVX instructions, and PD stands for packed double, so 4 double precision floating point values simultaneously. And you see in the first, it's move instructions, so you've got 4, I'm looking at the Lisp code, so you have 4 loads. Things are loaded from arrays. You have 3 add instructions, a single multiplication, 1 move instruction for storing the result, incrementing the loop, and that's it. So that's really almost the perfect code that you can write. And essentially the perfect code is over here produced by GCC, and the only difference is that GCC has also moved 2 of the load instructions into the add instructions, which is for some reason valid in x86 and also more efficient. And I was told that SBCL can now do this too. So the gap will finally close to 100%, just not for this talk. So there's now a peephole optimizer in SBCL too. And the cool thing is I ran some benchmarks. Mind that's before applying the peephole optimization. And indeed, I just ran those codes on the Lisp code, the C code, on a variety of architectures. I also uploaded the benchmark code on GitHub. And I computed how many gigaflops of performance can I achieve for that very simple benchmark on a variety of CPU architectures. And so, the important question, what's the ratio between the Lisp version and the C version? How close are we? How much did we manage to narrow the gap? And indeed, the gap has been narrowed to up to 94%. So we get 94% of the C code, at least on this particular AMD CPU. I've been stepping through the loop analysis frameworks. I really don't know why the difference is so large. Maybe someone can tell me afterwards. And this is quite satisfying, I think. And this is also where I want to show the live demo, because it's showing numbers is one thing. Wish me luck with mirroring this. Can you? Yes, wonderful. Oh, wow, that's what I get for putting my examples in Scratch. I just had to restart for that. Whatever, this narrow, the good thing is at least this way I finish in time. So I would just show the demo to interested people afterwards. That's how we finish the conference in time. So I can tell you what the demo would have shown is if you, which is fine. I mean, I'm a trustworthy person. I literally, it's that code over there. I could copy it from the slide and and put it there, but then you also need the benchmark loop that invokes it. So on this machine, I'm able to obtain 12 gigaflops single core performance. And also because some people have been asking me, so what's the difference between the regular Lisp code that ordinary people would write? And so if you just use CL loop, so instead of Lupus 4, and the difference is a factor of 20, so it's actually worth it. Hoisting, so it's a mixture of specializing, using SIMD instructions, and moving a lot out of the innermost loop. So, yes, I will just show that afterwards to interested people. So I also hope that there will be a discussion about that, about those results. So now we have auto-vectorization as a macro. And unfortunately, there is still a bit of work to be done. The most important thing is to integrate SBSIMD into SBCL. That's really the next milestone. And also, I hear people are eager to see ARM support, maybe even something in PowerPC. I haven't looked at that. So the architecture is relatively extensible. You have this table-driven design. So it shouldn't be so hard to add further architectures. And there's some cleanup to be done. The bigger chunk of work is Lupus. So the original idea was always that I just write something that works reasonably well, and I hope that other people find it so interesting that they help me finish it and make it to a proper framework, because usually you would do something called polyhedral optimization, and you do a lot of mathematical analysis. And so far, Lupus only has a knowledge about polynomials and does really stupid things and only works on nested regular loops. So inequalities are not so much handled. We are working we are working on loop splitting and unrolling and so forth. So there's infinite amounts of work that you can put in there. Anyone who has worked with loop vectorization, so this is the call for volunteers and also for discussion. Also, if you don't like the loop syntax, anything, just talk to me about that. And right, the conclusions. We have presented two libraries, SBSIMD and Lupus. The one makes it possible to use SIMD instructions in Common Lisp, at least on SBCL and x86. And we can now achieve more than 70% of the performance of high-quality C code, even in those cases where C is strong, which I think is really cool. And usually, Lupus can automate this conversion from scalar loops to SIMD vectorized loops. So in many cases, I'm thinking about image processing, maybe machine learning, and so forth. You could use Lupus to just get this factor of 4 to 20 speed up. And yeah, my main point is I'm looking forward to seeing others experiment with those tools. So I also had this discussion with a few from the few compiler people. So compilers are really good at making things, dumbing things down and making things more specific. But some transformations like vectorization are actually a generalization. They are adding abstraction. They are making the code more high level. And I'm not sure whether the compiler is always the right place to do so, because you have so little interaction. So you want to manually guide the compiler and maybe have annotations or domain-specific optimizations. And I think something like optimization macros would be a perfect fit for that. So the hope is that others are also encouraged to join this quest for optimizing macros. So the infrastructure is there. The type inference is a separate library. All those passes are relatively modular. So the hope is we can really have those domain-specific optimizations, and maybe this is the first step towards seeing much more of Common Lisp also in high-performance computing. And this is my final slide. So this is not my sole effort. So a lot of people have helped me in various ways. It's not a one-man project. So my special thanks, Convir is the competence network for scientific high-performance computing in Bavaria. They have funded this work. Also, Paul Kuong, whose blog posts were one of the reasons I joined. I decided that Common Lisp is a viable thing for high-performance computing. He has written the initial SSE SIMD support. Then Stas Bukharev, who added the low-level machinery for AVX and AVX2 and FMA to SBCL. All the other SBCL developers for the kind feedback. Then Bela Peksek, who has been an ardent user of SB-SIMD from day one, and he has also ported a few traditional benchmarks like n-body and spectral norms from C to Common Lisp, and he was spectacularly successful. So on this one benchmark side that I forgot to write down here, there's this one chunk of languages that are basically have the ideal code, and that's C, C++, and Common Lisp. And then there is a tiny gap, and then you have Rust. And then there is another gap, and then you have Julia. And this is so satisfying to see in the benchmarks. Of course, those are just a few benchmarks, but interesting times. Then the Erlangen Computing Center, they allowed me to benchmark on their systems, and Valentin, my intern, who is now helping with Lupus. Thank you very much. I apologize that there were some technical issues. And do you have any questions or remarks? Didier?
Okay, no mic. To what you will repeat?
If you're close enough to the question.
To what extent do you think this work could be useful in the language implementation itself, as opposed to just for user-level applications?
Okay, so the question is, to what degree do I think this can be used in language implementations itself? So I don't see this being used in, let's say, SBCL directly, so towards Common Lisp implementations, because it's just an additional maintenance burden. And something like vectorization, I think, will always be a bit experimental, and the SBCL developers are probably hesitant to add such experimental things into their compiler. So I think only the low-level machinery should be in there. But for experimentation of other languages on top of Common Lisp, this is immensely useful. So this is why I started it. I'm developing a programming language on top of SBCL and Common Lisp, and I plan to use that. Yes?
I saw a slide where you had the two loops. So my question is, how hard would it be to generalize the second loop to be just like the first loop, but without the suffixes, without the .4, .8, .32?
You mean this one?
No, back or this one.
Mm-hmm.
So to make it automatic, to generate the second loop automatically.
This is what Lupus does. So I wrote this a few times, 4 or 5 times, and I thought I'm doing the same thing over and over again. I'm going to write a macro that does that. So this is why I started Lupus. And Lupus automates this process. Yes?
Are there any alignment issues we have to take care of?
Very good question. The question was, are there any alignment issues to take care of? The good news is that on modern processors, unaligned loads are essentially as fast as aligned loads. The one exception is non-temporal loads in stores. I'm not going to explain that. Those people that need it, it's there. So Lupus understands non-temporal loads in stores, but then you have to worry about alignment, and I have no idea at the moment how you can specify the alignment of an array that you allocate with make array. Maybe someone can help me there. Thanks.
How much of the instruction set is supported? The instruction set for x86 is supported to show. Are they fully covered?
So the question was how much of the AVX and AVX2 instruction sets and all the SIMD instruction sets on x86 is supported here. And I would say 90% roughly. So there are some functions that are still missing, or I don't know what would be the Common Lisp equivalent, but almost all functions are there, also shuffles and permutations. Yes?
I'm not an expert in GPUs, but there's, if I understand something, you're reducing the number of instructions. You're optimizing by reducing the number of instructions executed. There's another way to increase performance, which is to optimize the memory latency using the local caches, the level 1, level 2, the multiple caches. Does your work go into that, or how would that presumed performance gap between Lisp and C be closed, in your opinion?
Okay, the question is about memory latency. I assume you are talking about cache blocking, and the like. So there is currently no cache blocking in Lupus. So it's really just inner loop vectorization, plain and simple. However, I'm working on this higher level parallel programming language called Lisp. And the plan is that Lisp will, among other things, it already does some local blocking, but also temporal blocking. So but this is not currently part of Lupus. But this is the most welcome addition. So if you are motivated to join this project, right? So there was another question in the back. Yeah. Okay.
Okay. So if Lupus is an auto-vectorizer and it works with no downsides, should that be something that compiler runs on every piece of code that resembles a loop, and that's it? Because for me, it really looks something that should be in a compiler pass, and it runs always, unless I'm missing something. It seems all automatic here.
That's a very good question. Why is SBCL not running Lupus? So for one, Lupus is very, very recent experimental work, as in the last commits have happened today. So at the moment, you shouldn't use it in SBCL. The other thing is that I make some assumptions. So Lupus is a domain-specific language. Maybe I should mention that. So in the loop body, only a special subset of common Lisp is allowed. For example, you cannot use tag body in there and a few other special forms, because I'm going for the simple 80% solution, 80% of the cases. So I have a much easier job than SBCL. Once you have unwind protect and arbitrary go-tos, you have different problems. I could solve them if you give me a decade of time, but I don't have a decade of time. So it's probably not yeah, I think this is the more maintainable approach to vectorization.
That's the thing that the GCC auto-vectorizer does. If it's too complex for some reason,
And there is something it doesn't like, just give up.
Yeah.
So I think from that point of view, you should just pattern match the code you see and see if it's in a form that you like. And okay.
So it would be wonderful if SBCL would do more of this work automatically, but even then there are implementations that definitely won't do that. So this is also why I wrote this as a portable library. So for example, this will also help people in CCL. You will not get automatic vectorization, but you still get the loop invariant code motion. So even the very simple Lisp implementations will benefit a lot from using Lupus. Yes?
You mentioned at the end that this feels less like something you want to do in a compiler, because a compiler makes things simpler, and this vectorization was actually extracting something and making it more high level. Is that the way I think about these things? It doesn't feel like vectorization seems like an implementation detail from the hardware. So I want to challenge you on that. How do you feel like it's more high level?
So people have the impression that SIMD is a low-level feature because it was introduced afterwards. So we've always been programming sequentially in C because we only had a single core with no SIMD, and then it was added later on. But in terms of a programming abstraction, it is higher level. It's like working on vectors instead of scalars. So you're really going upwards. You need some understanding also of what's happening. So without understanding of what's going on, you cannot vectorize. And many other compiler optimizations are just dumping things down, really.
Okay. Yeah, that sounds.
And this is also a pattern that I see frequently in compilers. There are some things that are essentially O of 1, where you can just narrow things down or log n or something. And then there are those things where you can spend infinite amounts of compute time on to slightly improve the result, and the complexity just goes up. And I think vectorization is one of these problems.
Right, because you mentioned that was also where you want a bit more interaction and not have to just have the compiler do something.
Yeah. And this is also an advantage. So I know that at least at our group, Some of our HPC codes have compile times of order of 10 minutes, 30 minutes. So it's not something to sneeze at. It's not negligible. And one of the reasons is that the compiler has to search a very wide space, while such macros, they are, compared to what the compiler does, they are insanely fast. It's a macro expansion.
Okay, thank you.
Okay, then other questions, I think, Philip?
Your Lupus is architecture independent, I gather, but the same cannot be said about SBSIM. If I write an image that uses vector instructions and then I want to run it on a machine that doesn't have vector instructions, will another function be called that doesn't use vector instructions, or do I get a fault, or what's the result here?
Okay, the question is rather, how would you create an image that runs both on architectures that have, say, AVX2 and that don't at the same time? And SBSIMD supports this. I was thinking about incorporating that into Lupus directly, that you make multiple versions and jump to them. But I think that was just overly complex. So I recommend that in this case you do it the other way around. You can tell Lupus which instruction set to use, and there is in SBSIMD there is an instruction set case macro that's really efficient, where you can select the available instruction sets at runtime. So you could write multiple versions using Lupus, and then jump to the best available one.
What if we delay the remaining questions until the...
Yes, I think.
But that means that you have to duplicate the loop bodies or the complete loops and have some kind of switch statement around it. How about providing some Lupus construct that provides multiple versions?
Sure, absolutely. So this is what I meant by I'm hoping for a discussion both about syntax and semantics of this. It's just very recent work.
Okay. Thank you, Marco, for the talk. And if you have additional questions for Marco about this, he's happy to talk about his work.